Okay, so welcome to lecture number 19, and today we'll talk about some features which are based on contour, which are left from yesterday's lecture, and then after those two features, we'll go for region-based features. Okay, how to extract the shape features by using region approach and so on. And initially, we'll talk about the remaining two features, like for example, chord distribution and Fourier descriptors, which are extracted based on the contour, and then after that we'll go for region-based features, like for example area, and then there are several features that we will study in today's lecture. So yesterday we talked about the bending energy and curvature as well as chain code and so on. So those features are extracted from this contour of this of shape and so on. So you know that for chain code, either you can go with 4 connectivity chain code or 8 connectivity chain code. So for this shape, this chain code is like this, and then curvature is nothing but, okay, you are taking the difference, this basically derivative of this chain code, so either positive or negative. So you got, okay, so from 0 to 0, this is 0 direction, and then when it go from 0 to 2, there, okay, 2 difference will be there, and 2 to 0 it will be -2, 0 to 1 it will be 1. So like that way you got this curvature, and from curvature you can obtain the bending energy by squaring of this curvature. So square of this 0, 0 will be 0, the 2 will be 4, -2 will be 4, and so on. So like that way, and finally bending energy is the summation of this one. So if you sum up this one, you'll get the bending energy. That is the feature of shape feature, which is derived from the contour and so on. So that is what we have studied in yesterday's lecture. Now also we talked about the signature, and for signature I told you that, okay, the normal contour distance which is calculated for each boundary point. Suppose, for example, if you have the point A, so if you mark the normal point on this one, so it will be B point will be the normal point, and this distance is okay, measured, and then it is plotted. So for every contour point, normal point is sought, and then that distance is plotted. So for example, for this circular object, if you consider this point, so normal point will be this one, so this distance is nothing but your diameter. So here again, if I consider this one, so normal to this one would be like this, so it will be same diameter. So for this circular object, for any contour point, this signature will be a straight line, whereas for a triangular object, this this will be like as a, for any point it will be it will form a triangular kind of shape and so on. So this is another feature which is obtained from the contour of the object, that is nothing but the signature. Then there are two more features based on the contour, that is, one is chord distribution. So chord distribution, you know that chord is nothing but any line joining in a line joining any 2 points of the region boundary is called as the chord. So this is nothing but the chord. Okay, so this point and this point, so if it is joining, so it is called as the chord. This point and this point is also called as a chord, and so on. So like that way, okay, so now this line is, okay, chord is making an angle of theta with this one, and then or if it is okay, you can also find the distance delta x and delta y like this way, or you can find, for example, for various angles. If you are considering this point on the boundary, and then you are finding the chord distribution with various angle, like for example with this angle, what is the chord distribution or chord length, like this way. For this angle, chord length will be like this way. For this angle, chord length will be like this way, and so on. So like that way, you, for various angle on every point on the boundary, you can find out the chord distribution. So this is okay, the chord length for various angles. For the next point, you can also find in the similar way. So like that way, you can find out the chord distribution as one of the feature for this one of shape representation based on the boundary length and boundary and so on, or contour and so on. So any line joining 2 points of the region boundary is called as the chord, and the distribution of the lengths and the angle of all chords on the contour may be used for the shape description. So like that way, as I explained, that you can consider any point on this boundary, and for any point you can find out the chord length for various angle. Like for this angle, what is the chord length, then for this angle, what is the chord length, and then next angle, what is the chord length, and so on. So like that way, for this boundary point at various angle, what is the chord length that you can find and that you can store as a this one chord distribution feature, and so on. Then again you can consider the next point on the boundary, and then you can find out the chord distribution, and so on. So like that way you can cover entire all those boundary points and find out the chord distribution, this one. So chord distribution feature, and so on. So the chord distribution can be computed as h delta x and delta y, which is nothing but integration of b of x. B of x is nothing but one point, and another point is nothing but x plus delta x or comma y plus delta y, and then you are integrating all those things. And in case of digital image, what you have to do, just you have to replace this instead of continuous domain, you have to use the discrete domain. So over you can consider this as a row, this kind of column, and then b of ij, and then this one. You can find the chord distribution in the similar way. So you can basically you can obtain the chord distribution in various way. One of the way is for every point you can find out with various angles what is the distance, and so on. So that can be used as a feature for this one. Then the next last this one contour based feature is nothing but the Fourier descriptor. Now you know that just 1 minute. See, in case of suppose for example you have the shape, okay, I don't know here. Suppose for example this is the shape, okay, and if you are representing that one in a spatial domain, so you know that this boundary will be having some x coordinate and y coordinate. This boundary point will be having some x coordinate and y coordinate. This boundary point will be, so all those boundary points will be having some x and y coordinates. So if you consider the x coordinate of all those boundary points, and then if you take the Fourier transform of that one, and also if you consider all those y coordinates of this boundary point, so it will form the vector, right? See that for every boundary point, okay, x coordinate of this boundary point, if you take it in this one vector form, so all those will be a single dimensional vector, one dimensional vector, and then after that you can find out the Fourier transform of that one. Similarly, all these boundary points will be having the y coordinates. So y coordinates, okay, of all these boundary points, if you can form in a vector, and then if you take the Fourier transform that one, so you'll get the Fourier coefficients in x as well as Fourier coefficient of y coordinates. And these Fourier coefficients basically can be used as a shape descriptor, and these Fourier descriptors can be like as a basically it can be rotation and scale invariant and so on. So like that way, see that suppose C is the closed curve in the complex plane, and traveling in anti-clockwise, this curve keep constant speed such that once circuit takes 2 times a period of complex z of t is obtained, where t is the time interval and the function has a period of t. It means suppose for example this any curve, like as this is the complex curve which is complete curve, and then so if you start from this point and then again if you come back to this point, so again it will start, so it will be repetition kind of thing, right? So this is the complex curve. So this permits Fourier representation z of t, okay, which is equal to summation over n t n e raised to int. So this is nothing but the Fourier transform basically, where the coefficient tn of series is called as the Fourier descriptor of C closed contour, and it is more useful to consider the curve distance s in comparison to the time t. So t can be replaced with twice by s by l, where l is the length of the curve and the Fourier descriptor tn is given by this equation. Or in digital domain, you can find out basically the coefficients, an coefficients and bn coefficients. And an coefficients, as I told you that, so for example, if you have this shape like this way, and every point on this contour will have the x coordinates. So if you can form the vector of that one, and then you can take the Fourier transform, which will, okay, Fourier coefficient an will give you the x coordinates Fourier coefficient. Similarly for y coordinates also, so you'll get an and bn as a Fourier descriptor basically from the contour of the object, and these coefficients an coefficient and bn coefficients are not invariant, but after some transformation, like as for example, if you take the magnitude of this one, so Rn can become a translation and rotation invariant, and for scale invariance you can achieve it by normalizing the things. So Fourier transform or Fourier descriptor of contour can be rotation, translation, and scale invariant, right? So how we have obtained, basically just we have taken this coordinates, like for example x coordinates and y coordinates of any shape. Okay, see that. So for example, this kind of shape is there, and then every point on this contour will have the x coordinate as well as y coordinates. So all x coordinates we can take in the vector form, and then we can take the Fourier transform that one. So that will represent an. Similarly for yn coordinate, okay, of all contour points, yn coordinates we can form a vector, and then that is nothing but the one-dimensional signal which we can take the Fourier transform. So that is the Bn. So we will get the Fourier descriptor an and bn from the contour of the this one, coordinates of the contours, and then from this an and bn we can obtain the invariant features by taking the magnitude of that one, and scale invariance can be achieved by normalization. So Fourier descriptor is also obtained from the contour. So these are the various features based on the contour which we can obtain for representation of the shape. Now so this part is over that is contour based shape representation and description. Now next part of this shape representation is based on the region. See, instead of considering only the contour or only the perimeter, we will consider the entire region, and from those region we can obtain the shape feature. So what are the different, basically what are the different features which can obtain from shape region based? So these are simple scalar region based description. Like for example, area is one of the features which we can obtain from the entire region. Second one is Euler number. Okay, then third one is projection. Fourth one is eccentricity. Fifth one is elongatedness. Then rectangularity, direction, and compactness. So these are basically simple scalar features which are obtained from the region. Then another features are there based on the region, like as a moments, then graph representation on the region skeleton, and region decomposition, and region neighborhood graphs, and so on. So in today's lecture, we will try to cover the maximum out of this simple scalar representation, that how to calculate the area from the region, how to find out the Euler number of the given shape, and so on, or projection, and so on, or eccentricity, and so on. So like that way, so we'll go with first one, that is the area. So area, like for example, area, so this is the shape basically, okay, and then how do you find the area of this shape? So you have to count how many pixels are there in the inside the boundary. So number of pixels, and if you know the resolution, that how much area is represented by every pixel, then you can easily calculate what is the total area of this shape, and so on. So like that way. So just what you do, you have to just count the number of pixels within the boundary. So inside the boundary, how many pixels are there? And if you know the resolution, so number of pixels multiplied by resolution will give you the total area of that this one. So this is very simple feature which we can obtain, but okay, since see, it may happen that there may be two different shapes and having the same area, so there may be confusion between these. So that is the difficulty with simple area based feature, like for example. And then convex area is like that. As I told you, that convex area is this object is the area of the convex hull that encloses the object. So this is the convex hull, okay, which is enclosing this object, and then total area of this one will be definitely more than the actual net area, because this area will be included in that, and so on. So sometimes people use convex area as also one of the feature. Sometimes people use the net area as one of the feature of the shape, and so on. So this is a region-based approach. So very simple approach. Just you have to calculate number of pixels within that region. So that is the simple thing. So this is for example original image, and then net area is this one, and then if you consider all those filled area, if you so those holes are fixed, and then you'll get this filled area, and so on. So you have basically option, either you can go with the net area or you can go with the filled area, depends upon your choice, and so on, right? So this is the simple features which we can obtain from the region-based approach. Then the second feature which we can obtain from the region-based approach is the Euler number. Now Euler number is also a topological feature, right? So what is basically Euler number? So this Euler number is nothing but number of connected components minus number of holes in the region. So how many connected components are there, in the region, minus how many number of holes are there. So Euler number is defined as the number of components, connected component minus number of holes. So this is the formula to calculate the Euler number of the shape feature, and so on. So this basically is simple topological feature which is invariant to translation, rotation, and scaling. But it may happen that sometime Euler number of two different shape may be same, so that may be a problem with this one. But advantage is that this Euler number is invariant to translation, rotation, and scaling. Now we'll see how to calculate the Euler number basically, right? So here, like for example, this is the image of vision, right? Now for this V, how many connected components are there? So this is entire one connected component. Is there any hole? No. For I, how many connected components are there? Two. See, this one and this one. So two connected components are there. For S, this is one connected component. There is no hole in that one. Again, for I, there will be two connected components. But for O, there is one connected component, this one connected component, and this is one hole, right? So H is one and C is one here in this case. For N, this is one connected component, but there is no complete hole. So for the entire image, how many connected components are there? For V, there is one connected component. For I, there are two connected components, so in total 3. For S, one more connected component, so 4. Then again, for I, there are two more connected components, so 6. For O, there is one connected component, that is 7, and for N there is one connected component. So total number of connected component in this image are 8, right? And how many holes are there? So only in the O there is only one hole. So C is 8 and H is 1. So Euler number of this entire image will be 7, right? Or you can individually obtain the Euler number of individual this letter also. For V, what is the Euler number? Euler number for V is 1, because number of connected component is 1 and number of holes are 0. So 1 minus 0 will be 1. For I, number of connected components are 2 and number of hole is 0. So for this I, Euler number will be 2. For S, again, it is 1. For I, 2. And for O, what is the Euler number? Number of connected component 1 minus number of hole 1. So for Euler number for this O will be 0. 1 minus 1, that is 0. For N, number of connected component 1 and hole is 0. So it will be 0. So for entire this image, Euler number will be equal to 8 minus 1, that is equal to 7. Similarly, see for this one, for this image, what is the, how many connected components are there? So entire this is one connected component, right? And then how many holes are there? There are two holes. One is this one hole and another one is this one hole. So what is the Euler number of this shape? That is one connected component minus this one. Two holes are there, right? Two holes are there. Now for this one, how many connected components are there? Entirely one connected components are there, and then number of holes are 0. For this one, how many connected components are there? 1. Number of holes are 0. Now, if you consider the entire this image, so number of connected components are this 1, 2, and 3. So this is 3. Number of connected components are 3. And in the entire image, how many holes are there? 1 and 1. So that is 2 holes. So this will be 2 holes. So the Euler number of this image will be equal to 3 minus 2. That is equal to 1. Right? So similarly, for example, if you take the A, okay, how many connected components are there? So basically 1 connected components are there, but in A there is 1 hole. So 1 minus 1, that will be equal to 0. Euler number of A is equal to 0. Similarly, if you consider the B, right? So number of connected components in the B will be equal to 1, and number of holes are 2. So 1 minus 2 will be equal to minus 1 will be the Euler number of B. Similarly, for C, okay, number of connected component will be 1, and number of number of holes will be 0. So Euler number of C will be equal to 1. So Euler number is basically translation, rotation, and scale invariant. But there may be, see that for A, like for example, there may be 2 letters which will be having same Euler number. Like for example, this one, A is having 1 Euler number equal to 0. Also Q 0 Euler number, or O also will be having 0 Euler number. So there are 2 images which are having the same Euler number, so that will make a confusion. So this is the problem with the Euler number. But advantage is that it is rotation, translation, and scale invariant. So this is another feature which can be used, which can be derived from the region of the shape and so on. Then the third feature, I hope that you have understood how to calculate the Euler number of the object and so on, right? Then the third feature is nothing but the projection. So from the shape, you can obtain the horizontal projection as well as vertical projection. So from that region, we can obtain the horizontal projection as well as vertical projection. And those projection can be used as a features in case of shape. So the projection of a binary object may provide useful information related to the object shape. So it can be found by summing all pixels along the rows or columns. Okay, if you are doing the summing along the rows, it can be called as a horizontal projection. And if you are doing the summing along the column, it's called as the vertical projection, right? Now see that, mathematically it can be represented as projection can be defined as a horizontal projection HIR. You are just making all the pixel summation of pixels along the rows, right? And for vertical projection, you are making all those summation of all those pixels along the column. So this is the mathematical formula for calculating the projection in horizontal direction and this projection in the vertical direction. All right. So just look at this one. You'll find that, suppose for example, this is the image, right? So along the column, vertical vertical projection. See that one means basically the this one object area. So this is the object area. 0 is background, right? So what is the basically object area along column? So here there is no 1, so it will be 0. What about this one? There is only 1, so it will be 1. What about this one column? So this will be 1 plus 1, that is equal to 2. For this column, 1 plus 1 equal to 2. For this column, 1 plus 1 plus 1 plus 1, that is 4. So like that way, you are just making the projection in vertical direction along the column. So that is vertical projection, which will come here like this way. So for this column, it will be 1 plus 1 plus 1, that is 3. There is no object here, pixel here, so it will be 0. For this will be 0. So vertical projection for this object will be like as a 0, 1, 2, 2, 4, 4, 3, 0, 0. Similarly, for horizontal projection, you are making the summation in the horizontal direction. So see that how many ones are there in horizontal first row? Only 1. For second row, this 1 plus that is 1, that is equal to 2. For third row, 1 plus 1 plus 1 plus 1 plus 1, that is 5. Right? For fourth row, it will be 6. For fifth row, it will be 2, 1 plus 1. And then for this one will be equal to 0. Right? So this is the horizontal projection. If you are making the summation in horizontal direction, that will make the horizontal projection. If you are making summation in a vertical direction, like as a column wise, then it is okay, vertical projection. So this is the vertical projection of this object, and this is the horizontal projection of the object. So this can be used as a feature for this one. I hope that you have understood how to calculate the projection, right? From the image also, you can see that like this is the object, okay? And okay, so these are the pixels in this object. So this will be the vertical projection. You are making basically the summation along the column, okay? So like that way. So if you make so this in this one, then will be there only 1. So this one, there will be 2. In this one, 1, 2, 3, 4, and 5. So like that way. And then here it will be 1, then 2, 3. So 3 will be there. And in this way, 1, 2, 3, 4. So this will be 4, right? And in this, okay, it will be only 1. So this will be the projection in this direction. And if you go in this direction, so how many are there? 1, 2, and 3. So this will be 3. What about this one? 1 and 2. So 1 and 2 here. What about this one? Again 3. So 3. What about this one? 1, 2, 3, 4, 5, and 6. So it will be 6 unit. And then 1 and 2. So this will be 2. So this can be called as the horizontal projection or vertical projection, and so on. So like that way, you can obtain the projection of the given object. Simply, okay, this is very simple. Like just you have to count the horizontally how many pixels are there, and vertically how many pixels are there. So vertically it will give you the projection, vertical projection, and horizontally it will give the horizontal projection. So which can be used as a feature for this one, right? The next feature is eccentricity. Okay, so eccentricity is like that. For example, you have the shape like this. Okay, so you have this major axis and minor axis. So see that this is the major axis A and this is the minor axis B. So the simplest eccentricity characteristic is the ratio of length of the maximum chord A. So this is the maximum chord A and maximum chord, minimum chord B. So maximum chord, it is the ratio of maximum chord A to the maximum chord B here, which is perpendicular to the A basically. So this can be used as a so ratio of A by B can be used as a feature in case of this one region-based approach. So another approximate eccentricity measure is based on the ratio of main region axis of inertia and so on. Right. Then elongatedness is next one. See that. I hope that you have understood what is by eccentricity. So eccentricity is nothing but the maximum chord, okay, length of maximum chord A, and then perpendicular this okay, chord B. So just you are taking the ratio of that one, right? Then elongatedness is next feature which can be used. So in its simplest form, elongatedness is the ratio of length and width of the object bounding box. Like for example, if you, so for example, this is the shape, and then if you okay, fit it in a bounding box like that way, okay. So suppose for example, this is the bounding box, and then what is the length, maximum length and width of that one? So that ratio can be used as elongatedness. So or here might, okay, I don't know, okay, right, this is the bounding box, right? So suppose for example, this is the shape, and then this is the bounding box which is including this shape. So this length divided by width is nothing but the elongatedness, okay. Feature can be calculated as a, you know, the ratio of length by width. So this shape is having high elongatedness, and then this shape is having low elongated because width is more as compared to the length, and then like that way, Okay, so elongatedness is, so it is the simplest form of okay, elongation is the ratio between the length and the width of the object bounding box. So elongation is equal to width bounding box divided by length of the bounding box. The result is a measure of object elongation, and this gives the value as value between 0 to 1, 0 and 1. So if the ratio is equal, that is the if your length and width are equal, then it will be okay, object will be square or circularly shaped, and as the ratio decreases from 1, so at that time your value will be equal to 1, elongation value will be equal to 1 if width and length is same, right? So definitely for square object it will be width and length will be same. Also circular object also width and length will be same. So for square and circular object this elongation will be 1. For other objects it will be less than 1. So as the ratio decreases from 1, the object becomes more elongated and so on, right? So this criteria cannot succeed in a curved region for which the elongation of elongatedness must be based on the maximum region thickness and so on. So sometimes also elongatedness can be evaluated as the ratio of region area and the square of its thickness. So area divided by 2d square, where the d is basically the maximum region thickness, holes must be filled up in present case, can be determined as the number of d of erosion steps that may be applied before region totally disappears. So another way it can be calculated as area by 2d square. Okay, and so this is basically okay, one way is basically length divided by width. Okay, if you basically this is the shape, and then if it is you know, okay, inserted in the bounding box, so bounding box length divided by bounding box width, that will give you the elongatedness and so on. Then eccentricity is the last feature which we will study today. So eccentricity is the ratio of the length of the short or minor axis to the length of long or major axis of an object. So eccentricity is given by axis length short divided by axis length long. So the result of a measure of object eccentricity is given in between 0 to 1. So sometimes it is called as the ellipticity also. Like for example, what is the high eccentricity? Length of major axis divided by minor axis. So this is the shape having the high eccentricity, and this is the shape having the low eccentricity, because this major axis length and minor axis length is almost same, so it will be low in that case, whereas in this case it will be high. So eccentricity is calculated as it is the ratio of major axis to the minor axis, right? So and okay, regularity, we will see regularity in our next lecture, and the remaining feature also based on the okay region we'll see in the next lecture. So what we have studied in this lecture is that okay, the remaining two features like this one, chord distribution and Fourier descriptor on boundary based, and after that we studied in this chapter in this lecture as simple scalar region description, like as an area, just by finding the all pixels or summation of all pixels, then Euler number, that is equal to connected components minus number of holes, then projection, horizontal and vertical projection, then eccentricity and elongatedness. So that we have studied in this lecture. In next lecture we'll study the rectangularity, direction and compactness, and then moment and so on. So today we'll stop here. I hope that you have understood this simple scalar based features, and as well as remaining features like as Fourier descriptors, just we have calculated from the contour and so on. So that is what okay we have studied in today's lecture. Okay, so we'll stop today's lecture here.